Hello and welcome again to my Physics Online video lecture series. Today's video, we're going to be talking briefly about the motion of a charged particle in a magnetic field. So, in order to do that, I'm going to be pulling open my little sketch pad. And what we know at this point is that the force on charged particle is given by from a magnetic field is given by FB is QV cross B, where B is the magnetic field. And that essentially means that the force from the magnetic field is perpendicular to both the velocity and the force from the magnetic field is perpendicular to the magnetic field. So now what we want to do is consider what would happen if you had a charged particle that was entering a magnetic field. Let's say that the magnetic field happens to be pointing into the plane of the screen, like so. So I have basically this uniform magnetic field, and it has some charged particle that is going to enter into it. For example, maybe the particle at this moment in time is right here with this upward velocity vector. Okay, well, that basically means that the force acting on the particle moving upward, and then point your fingers out of the screen away from you, and your thumb will point in the direction that the force is acting on this particle. So there's a force in this direction from the magnetic field. Well, since that force is perpendicular to both the velocity and the field, it essentially implies that what this particle is going to end up doing is kind of following a path more or less like this within the magnetic field. Essentially, at each point on this path, the particle is going to have some particular velocity, which is tangent to the path, and it's going to have some force which has to be perpendicular to both the velocity and the magnetic field. These forces always point towards the center of the circle. In fact, this magnetic field force is essentially a centripetal force. So it's a center-seeking type of force. And you'll recall from Physics 1 that centripetal force is mass times centripetal acceleration, which is mass times speed squared divided by radius, or if you prefer, mass times omega squared times r. So the radius is defined just as the radius of this curvature. Now, a slight caveat to this: what would happen if the particle, instead of having a velocity totally perpendicular to the magnetic field, as in this picture, what if the velocity was like, rather than just straight up, what if it was like up but also slightly out of the page? How would that affect things? Well, essentially what we would need to do here is denote that v in this case is the perpendicular component of the velocity with respect to the magnetic field. So v perpendicular is just perpendicular to b. And so there may be also a parallel component. The parallel component is unaffected. And in this case, your particle's trajectory will basically be helical. So instead of just being a circle, you'd end up with a helix more or less like this, as the particle is passing through this magnetic field. So if I draw the magnetic field lines again, basically it's moving about these magnetic field lines like so. And again, we could go and change this equation, coming back over here to these sets of equations. This one right here basically is saying that the magnetic field FB is Q times V perpendicular times B, or if you prefer, you could call that Q times V times B times sine of angle between B field and between velocity and B field. So phi is angle like this. So here's V, here's V and B. Phi is this angle right here. Okay, so over here, same thing would hold true. We just would happen to have a general drift speed in this direction right here, V drift, which would just be the parallel component. Let's write that here. V drift is V parallel. V is V parallel plus V perpendicular. Okay. Now coming back over to these equations, we can combine the equations to get something like what the radius of curvature is. So using the fact that we have, on the one hand, FB is V, let's do VB or QVB sine phi. And on the other hand, FB is mv squared over r, or V sine squared phi specifically, over r, because V perpendicular is V sine phi. Put these two equations together, and what you end up getting is QVB sine phi is equal to mv squared sine squared phi over r. And so you can solve these for the radius of curvature for the circle, and what you get is that r is equal to m times v squared times sine squared phi divided by q times v times b times sine phi. And so if you simplify your terms by canceling stuff that's common to top and bottom, you get r is equal to mv over qb sine phi. And that's your radius of curvature for the motion. The second thing that you can do is, again, recall that this FB was also m omega squared times r, or specifically m omega squared sine squared phi, this one being your V. And again, FB was Q times V times B times sine phi. So if you put these two equations together, you have m omega squared r sine squared phi is equal to QVB sine phi. And that means that omega squared is equal to Q times V times B times sine phi divided by m r sine squared phi. Making that substitution for r that we had on the previous page, you'd have QVB sine phi divided by m times, this is mv over qb sine phi sine squared phi. So now we essentially can cancel some like terms. We got sine phi's in both places. We've got Q and B would actually kind of come up top, and we've got V and V. And so we end up with omega squared is equal to Q squared B squared divided by m squared sine squared phi. And that means that omega is QB over m sine phi. Omega can also be translated into the period, how much time it takes to complete a one cycle, one circular orbit, if you will. And so what you end up with for that, oops, I left off some, whoops, I'm putting in some extra stuff here. What you end up with that, t is 2 pi over omega. So you'd end up with 2 pi m sine phi divided by qb. This is the period of cycle, or cyclotron. Is called cyclotron period. This over here is called cyclotron radius. Okay, and again, we're using the fact that period is 2 pi divided by omega. That's from simple rotational dynamics. It's also from the spring oscillators, oscillations, waves, that stuff. So oscillations, waves, periodic motion in general, orbits. So this is a kind of review equation. Okay, so actually now we have the total motion of this charged particle in the field. So we can do a quick example. Right, so our example is that we need to determine the cyclotron radius and period for a 1.05 picocoulomb particle of mass 3.15 grams, which is moving at a velocity of 300,000 meters per second in a direction perpendicular to the magnetic field of magnitude 0.4 teslas. So the first part was to determine the cyclotron radius. So that is using this equation, mv over qb sine phi. So we have mv sine phi over qb. So the q is right here, the m is right here, the v is right here, the b is right here, and the fact that it says perpendicular, this means phi equals 90 degrees. So what we have is 3.15 times 10 to the minus 3 kilograms. We would want this in kilograms. We would want the speed in meters per second. So that's 3 times 10 to the 5 meters per second divided by Q, which is 1.05 times 10 to the minus 12 coulombs times the magnetic field strength of 0.40 Tesla. Okay, so this ends up being about 2.25 times 10 to the 15 meters. So that's a pretty huge radius. That's actually a sort of unusually large radius, but this is a fairly large object. If you had an individual particle where the mass is maybe 24 orders of magnitude smaller, and the charge is only 7 orders of magnitude smaller, then you're knocking off about 17 orders of magnitude from this. About 2.25 meters for your radius. 2.25 centimeters for your radius in that case, which is fairly typical for particle detectors. What about the period? Well, that's using this equation. T is 2 pi m sine theta over qv. So all right. So 2 pi m sine phi q over b is 2 times pi times mass, which is 3.15 times 10 to the minus 3 kilograms. Sine 90 degrees will just be 1 divided by Q, 1.05 times 10 to the minus 12 coulombs times B of 0.40 Tesla. So plugging all of that into our calculator, let's see, 6 pi over 0.4, so that would be basically 15 pi times 10 to the 9 seconds. So we could say maybe like 1.5 pi or 4.5 something times 10 to the 10 seconds. Okay, and that's it for today's video. Thanks for watching, and I hope you learned something from it.